So we've focused on the acid reaction, but we know, because we've designated this entire categorization of chemical reactions as acid-base reactions, that we have to look carefully at the base side of this whole story. And there's a bias toward concentrating on the acidic side, in part because the donation of that H+, that proton, to form H3O+, is actually a fairly simple process in a reaction in which we simply put the acid into the water. But we have to look at the whole breadth of reactions as they apply both to the physical sciences, to the life sciences. It turns out that reactions that form a base are extremely important to living systems. In fact, human blood is basic in character, but so too are the global ocean systems. In fact, as we'll see, the pH of blood and the pH of the ocean are actually very close together, and there's an evolutionary reason for that. But for our purposes here, we need to bring symmetry to this discussion of acids and bases. So let's write out a reaction between our favorite solvent, water, and a base, which we will assume is in the aqueous phase. And when we put that base into water, it successfully steals a proton from water, and it leaves that water as a hydroxide anion in solution and our BH plus in aqueous solution. That's our base. So let's analyze first. We start with water, which in this case is an acid, and we form a hydroxide anion that is a base. In the same vein, we start with B, which is our base, and we form a conjugate acid as a product. So again, we have this symmetry between an acid and its conjugate base and a base and its conjugate acid. And we always keep an eye on that relationship. But now we're interested in expressing this from the point of view of the reaction, the formation of the base. And so the base dissociation constant, or base ionization constant, we can now write out in its general form. That's equal to the formation of BH plus times the concentration of the hydroxide anion divided through by the concentration of the base. And remember that those concentrations refer to the state of equilibrium. That is, after we've moved down the Gibbs free energy surface under non-standard conditions until we found the equilibrium point. Let's continue our discussion of basic systems, that is, reactions that form a base when we put the base into water. And we also come back to the same expression for the product of H3O plus and the hydroxide anion. And this expression is equally valid when we're analyzing acid reactions as when we're analyzing base reactions, because the release of Gibbs free energy in the reaction of H3O plus and OH minus forming water is so powerful that this expression dominates under all conditions. And so we know that's 1 times 10 to the minus 14, and we know that that's K sub W, the equilibrium constant for water. But here's the crucial point. The details of how a particular combination of acids or bases is added to a solution is irrelevant. I state that again, irrelevant to the calculation of the product of H3O plus and OH minus, because the release of free energy in that reaction overwhelms any other process, and it dominates, it dictates the fact that the product of H3O plus and OH minus is always 1 times 10 to the minus 14 at 298 Kelvin. Okay, so let's diagram this. This is quite interesting. So let's take the neutral case. This is the case where we've got pure water, and as we know, the concentration of H3O plus and the concentration of OH minus exactly balance. And they exactly balance because their product has to be 1 times 10 to the minus 14, and in that case their concentration is 10 to the minus 7, identically for both. But now let's move to an acidic case. Let's suppose we put a strong acid into water. Now, one thing that remains fixed is the equilibrium constant for water. That's never altered. But the relative concentrations are dramatically different. H3O plus for a strong acid, in this case 10 to the minus 1 molar, and OH minus is 10 to the minus 13 molar. So now we've shifted dramatically the ratio of H3O plus to OH minus, but the product stays the same, and the product stays the same again because the Gibbs free energy diagram for the reaction of H3O plus OH minus, that equilibrium reaction forming water has a release of Gibbs free energy that we've calculated before. That release of Gibbs free energy is minus 79.9 kilojoules. So whopping release of Gibbs free energy, and that drives that reaction to the right-hand side. And so anytime H3O plus and OH minus are in solution, they will react in order to satisfy that Gibbs free energy diagram. So now we have to look at the case for inserting a base into solution. Now in this case, we put a strong base in, we can achieve a 10 to the minus 1 molar OH minus concentration. But that tells us immediately, because the product of OH minus and H3O plus is locked to 1 times 10 to the minus 14, that the H3O plus concentration decreases to 10 to the minus 13 molar. And again, 10 to the minus 13 times 10 to the minus 1 gives us our equilibrium constant for water. So the next point in analyzing the base reactions is that we emphasize the fact that a base dissolved in water extracts a proton from water. It steals a proton. And just as the case for acids, the operator p on any number gives us minus to the log base 10 of that same number. So that means minus log to the base 10 of OH minus is equal to POH. We also know that we can write the base equilibrium constant, K sub B, that's equal to the hydroxide anion concentration times the formed BH plus, resulting from the transfer of that proton from water to the base B, and we have to divide that through by the concentration of the base after equilibrium has been achieved. We can then write P, the operator, on the base equilibrium constant. That's simply equal to minus log to the base 10 of that base equilibrium constant. So we have a consistency here. We use the operator P as minus log to the base 10 of whatever the quantity is, and we uniformly apply that throughout. Now let's look at a condition for increasing strength in the concentration of OH minus, that is the increasing strength of the equilibrium that shifts toward the product OH minus. And so with increasing strength, we recognize that K of B, which is equal to OH minus times BH plus divided by the base concentration at equilibrium, with increasing strength, the concentration of OH minus increases, and that drives up the value of the equilibrium constant for that base. So the stronger the base is, the larger that equilibrium constant. So we finally point out that when we have conjugate acid-base pairs, we have the condition where a strong base has a weak conjugate acid, and a weak base has a strong conjugate acid.